Hi everyone, this is Steve Christensen. Today we're going to talk about Chapter 3, Coagulation and Floccuation. Suspended solids. SS is the acronym. So we have different types. We have settleable, which is like dirt and sand and things like that. And then we have non-settleable, which is colloidal matter, which is bacteria, fine clay, and silts, and they really don't like to settle out. So this is a little graph that kind of puts that in perspective. You know, when we look at the top, gravel, 0.3 seconds to go ahead and go, 1 feet deep and settle down. Pretty quick. And then you look at the progression. Coarse sand, 3 seconds. Fine sand, 38 seconds. Silt, 33 minutes. But then let's look at what's considered non-settleable. Bacterias, 55 hours. I want to point out this. This is the log removal. It's a 3-log removal right there on that is what that says. On color, 230 days. It's a 4-log removal. Colloidal particles, 6.3 years. And again, you go ahead and keep moving on to some of the other colloidal particles. It could take up to 63 years. That's pretty just staggering. So what is a coagulant? A coagulant is a chemical that causes fine particles in the water to clump together into larger particles. It's primarily due to the electrical charge of the particles and the coagulant. We start messing with the polarities of the pluses and the minuses. And we go ahead and that allows them to go ahead and clump together. And that's what we want. When they clump together, then they gain weight. And eventually then they'll settle out. So what is coagulation? It's easier to separate particles from water by settling, filtering, skimming, or draining. A streaming current monitor, it measures the gross electrical charge of the water. And again, we know a battery has 2 ends to it, a plus and a minus. Well, all these little particles around have pluses and minuses, and some are actually neutral also. But the streaming current monitor is a continuous reading electronic device, and it can be used to control the coagulant feed pump. And it's used to optimize the coagulant dose. The dose is how much we're putting in. Flash mixing. When we put in this coagulation chemicals, we mix the water. It's got to mix in with it. And so we have different types. We have hydraulic mixing, which is done by the water flow. We have static mixers, which are sloping vanes within a mixer. We have mechanical mixers, which are paddles, turbines, and propellers. We have baffled chambers, which provide turbulence. Diffusers, which are perforated tubes. Pumped blenders, which is a diffuser in a pipe. And inline mixers. There's an inline mixer right there. And what happens is, these ports are your chemical feeds. The water goes through and it hits this diffuser, and it's an inline mixer, and it automatically just churns the water and mixes things up. We have a flash mixer. And again, they come in all different styles and shapes. You can see the diagram on the right has some paddles, little propellers rather, and the one on the left has wooden slats that act, and basically it stirs it around nice and slow. Baffled chambers. We can put the water through baffled chambers, which will do the same thing. An upflow clarifier. Well, what's going on here? Okay. Well, we've got, basically our water coming in, which is our raw water. And the water comes in, and there's a chemical injection here going on. It comes down, and it mixes in this, and then it goes up, and it spills over the weir into the clarified water. So it's cleaner. Things have floated to the bottom, and then we have our fluent where it goes out. We have an influent and an effluent. Effluent is where it goes out, influent is where it comes in. And also you can show your raw water coming in over here. We have our agitator up here, which is again stirring it in a primary mixing zone. So coagulation and the types. Primary coagulants. They neutralize the electrical charge of particles in water, and it allows them to clump together and, again, gaining weight. Coagulant aids add density to slow settling flock and adds toughness so the flock will not break up, which is called shearing in the process. Sometimes clay and sand can also be used. Coagulant types and the complex theory. Metallic salts. We have aluminum sulfite, ferrous sulfite. They create a series of reactions within the water and other ions in the water, resulting in flock. The reactions are due to opposing electrical charge of coagulant and particulates. Flock adsorbs to turbidity in the water. So coagulation aids. We have synthetic organic polymers. They're cationic, which means positive charges, which is the most common, anionic, which is a negative charge, and non-ionic, which is no electrical charge. You need to know those terms. So how does it work? We add our cationic polymer in, it charges, it neutralizes things and destabilizes the colloid. And then we form microflock, which is where it's starting to clump together. The microflock then is mixed with a polymer, and it's mixed up a little bit, and we get our macroflock, which is, again, the big group of things that's going to gain weight, and is going to want to settle then to the bottom of those clarifiers. Considerations when using a polymer. Some polymers lose effectiveness when chlorine exists in the water. Some polymers are dosage limited. Overdosing adversely affects coagulation and efficiency. Overdosing accelerates the head loss buildup, and not all water supplies are treated with equal success. Again, we have all these variations in our water, and it's all over the board. So basic chemistry. Coagulation, the definition is the physical chemical reaction between alkalinity and a coagulant, and that forms your flock. The proper pH must be maintained, which again is 5 to 7, slightly acidic. A residual alkalinity prevents pH from changing. Neutral and lower pH waters favor positive flock. Alkalinity is the capacity of water to neutralize acid. The operator has no control over your source water. You're going to get what you get. I drove by New Maloney's yesterday, and with all these storms going, it looks like chocolate milk, let alone the fact that there's huge debris flows going. So we have all kinds of things, and an operator obviously has no control over that. The proper selection of a coagulant and polymer is critical. So what is floccuation? Create a flock of good size, density, and toughness for removal by sedimentation and/or filtration. Floccuation provides slow, gentle agitation of the water in the coagulation. It transforms smaller flock formed by the flash mix into larger flocks. The rate of flock growth depends on the rate that the smaller flock collides. Larger flock are more fragile, and slow mixing is really important to reduce shearing. There's that word again, shearing. You need to understand that. Water is slowed to reduce short circuiting. So there's a big commercial mixer. You can see those big paddles, and they go around. So efficient floccuation. We want adequate stirring time, which equals the detention time. The correct stirring intensity, mechanical or means of stirring, and the correct basin for uniform mixing. Lack of adequate flock formation can result from inadequate flash mixing. Mixing should take less than 1 minute, but be thorough. So on your flash mixing, it's a fairly intense mix that happens, but then it needs to slow down because you're starting to get those things all clumping together, and if you don't slow it down, it'll break apart. Again, that's shearing. Improper floccuation mixing. Long and gentle mixing must bring smaller flock together. Inadequate floccuation time should take 10 minutes to 1 hour with an average of 30 minutes. So you can see how this slowed down quite a bit. So what are some of our operational controls? We test for pH, coagulant and aids that work best in a particular pH range. And again, alum, which is one of the most common coagulants used in this industry, is a 5 to 7 pH. Again, slightly acidic. Turbidity is the measurement of raw water, and post-sedimentation basin is crucial. So we always are looking at our turbidity, water going in, water coming out. Okay, and that, our turbidity, again, it's all those things floating in the water. So we really measure our turbidity a lot with those streaming current monitors. We have those several places throughout our plant. We also do jar tests in the lab, which are used for determining the best coagulant dosage. There's a jar test. A jar test is really a miniature version of your water treatment plant. And what you do is you put different chemical doses in, and you basically, graduate them, and it allows you then to find out through this process what your ideal dosage will be. So again, process controls, measured filter water turbidity, okay, that's a little turbidimeter up there, and you basically fill these little vials, you slide it in, and they work off reflected light, okay? So again, we're talking about all that stuff in the water. Visual observation, jar tests, and lab tests. And again, many styles. This is an inline one. This is a portable one you can take out in the field. Laboratory tests for process performance. Temperature, pH, color, alkalinity, and turbidity. Turbidity. It's the indirect measurement of suspended solids and concentration of those solids. And again, it gets into light and the reflection of light, and that's how that tool works. Coagulation dosage. The dosage is determined by the jar test. Multiple liter jars are filled with raw water, and we want to use representative samples only. It's placed on a mixer to imitate a flash mix. The coagulant is then added in milligrams, and the water and the coagulants are mixed. The mixer is turned off, and the observed settleability, and you determine the best dosage in milligrams per liter to apply to the system. So we're looking at settling conditions, detention times, and mixing conditions. We want to certainly prevent overdosing. The use of chemicals actually is used, not reagent grade chemicals. Use chemicals actually used, not reagent grade chemicals. Troubleshooting. The usual culprit in sudden filtered water turbidity is poor coagulation and floccuation performance. Milky bluish tint in the water is an overdose of alum, aluminum sulfate. Consider the process change when changes in the source water quality, changes in the coagulant base and effluent, and changes in floccuation base and effluent. Again, we're measuring, through our turbidities, these different points in the system. Enhanced coagulation, designed to remove or reduce more efficiently natural organic matter, DBPs, disinfection byproducts, and THMs, trihalomethanes. Dissolved or suspended organic carbon, which is color, and total organic carbon, which is your TOCs. So how do we enhance coagulation in lower pH? Floccuation improves at lower pH levels, which is optimum. Sulfuric acid addition prior to the coagulant preconditions of organic compounds, it preps for the flock. How to lower the pH? Coagulant demand decrease correspondingly to the degree of molecular dissociation at the lower pH. Humic and fulvic molecules dissociate or separate to a lesser degree at lower pHs. Communication, part of the coagulation floccuation process. When changing shifts or working with others, always discuss. You want to keep really good records, and these plants all have logs, both manually and electronically. There's backup redundant systems in the record keeping. You want to use clear and concise oral communications, unique or unusual events you want to make sure they note, and current process conditions. A lot of supervisors require that their operators actually keep daily journals. And again, you're looking for trends and this kind of thing that when there's a shift or somebody leaves or somebody gets hurt and they're off the job, that record keeping is key to keeping that system moving in a good direction and with a knowledge base that's out there. Hazards of coagulation and flock equipment. Well, this is a pretty funny one, I think. Touching wires causes instant death, and then they're going to fine you $200 after you're dead. But anyway, we know there's electrical hazards, certainly. We're working with water and big swimming pool size holding tanks and clear wells and all that kind of stuff. So there's certainly drowning hazards. Mechanical equipment, we have things that are moving, and we have confined spaces. And again, we've talked a little bit about confined spaces, but again, you need to understand certainly it's toxic and explosive gases, it's insufficient oxygen, and you'll always want to use atmospheric testing equipment. So hazards when working in the laboratory include glassware, dangerous chemicals, acidic solutions, base and caustic solutions, and reagents. Okay, we want to go ahead and make sure we always have our personal protective equipment on, our PPEs, which it could be a smock. We're talking definitely safety glasses or a shield. Again, depending on what you're doing, gloves, numerous things, but you always want to make sure that you're doing things safely. Okay, great. Well, that's the end of the lesson today. I hope everybody got something out of that. And again, you want to go ahead and review these things, and especially if you're going to be testing. Hope everybody has a great day. Bye-bye.